You pick up two magnets, push them together, and there's this invisible something pushing back. Flip one around, and snap they slam together so hard they almost take your finger off. What's that? What's actually happening there? Well, when you ask why about anything, you need a place to stand. You need things you already accept as true. Otherwise, you're just falling forever with why it never ends. Let me show you. Why is your Aunt Minnie in the hospital? She slipped on ice and broke her hip. Okay. But why did she slip? Because ice is slippery. Everybody knows that. But why is ice slippery? That's actually interesting. When you stand on ice, the pressure melts a tiny layer on top. So, you're really sliding on water. But then, why does pressure melt ice? Because water expands when it freezes one of the few substances that does that. So, pressure wants to unexpand it. But why does water expand when it freezes? And why did she fall when she slipped? That's gravity. Now, you're into the planets and the whole universe. Why does falling hurt? Why did her husband call the hospital? Because he cares about his wife. Does he, though? Not all husbands do when they're drunk and angry. You see what's happening? Every answer opens more questions. You have to stop somewhere, or you'll be asking why until you collapse. People want me to explain magnets in terms of something familiar, something they already understand. Maybe rubber bands. Maybe there are invisible rubber bands connecting the magnets, pulling them together. But that's cheating. If I tell you that you'll be happy for 3 seconds, then you'll ask, why do rubber bands pull back? And I'll have to tell you about forces between molecules, which are electrical forces, the same forces I'm trying to explain. So I'm running in circles, using the mystery to explain the mystery. That's not understanding, that's a con game. Electrical and magnetic forces are fundamental. They're bedrock. We don't explain them in terms of something else. We explain everything else in terms of them. Chemistry is electromagnetic forces between atoms. Biology is built on chemistry. The chair holding you up right now electromagnetic. Your whole body not falling apart electromagnetic. It's everywhere. It runs everything. But here's something funny. You don't think it's strange that you can't put your hand through a table. You push on its back. Totally normal. You've done it your whole life. But your hand never actually touches the table. No, really. The atoms get close, and the electrons start repelling each other. That's what you feel as solid. That's what touching is. Same force, exact same force as the magnets. So why is the table obvious and the magnet mysterious? Just because you grew up pushing on tables and not pushing magnets together every day. The table is just as strange, you just stopped wondering about it. Electrical forces aren't just strong, they're monstrously strong. Compared to gravity, electromagnetism is stronger by something like 1 followed by 40 zeros. I don't even know the name for that number. It's not much stronger, it's incomprehensibly, absurdly stronger. So why don't we notice? Because atoms are balanced. Positive charges in the middle, negative charges around the outside, plus and minus. Everything neutralizes. The most powerful force in nature hiding in plain sight because it cancels itself out. When you comb your hair and pick up bits of paper, you rubbed off a few electrons, just a few. But the force is so gigantic that even that tiny imbalance creates something you can see across the room. And magnets are special because of what happens in iron. And in most materials, they spin every which way. chaos. It all cancels. But in iron, they line up, all spinning the same direction. And when they cooperate like that, all those tiny magnetic effects don't cancel anymore. They amplify. And suddenly, you've got something you can feel from far away. That's why iron is magnetic and copper isn't. Copper has the same physics, same electrons, same forces, but the spins point randomly. In iron, they work together. It's like a stadium full of people. If everyone talks at once, you hear noise nothing. But if everyone chants the same word, you hear it miles away. Same voices, completely different effect. Now, let's go deeper. What's actually happening when two magnets pull toward each other? At the most fundamental level, it's about particles being exchanged. See, electrons don't just sit there. They're constantly throwing things at each other. Photons, little packets of light. And I don't mean lights you can see. These are what we call virtual photons. They exist only during the interaction. You can never catch one and look at it directly. One electron throws a photon, another electron catches it. And that exchange is what we experience as the electromagnetic pull. It sounds strange, right? Two things pushing or pulling each other by throwing stuff back and forth. But that's exactly what's happening. Every time you feel a magnet push against another magnet, trillions upon trillions of these virtual photons are being exchanged between the electrons in both pieces of metal. And here's the beautiful thing. Everything electromagnetic comes from just three simple actions. A photon goes from one place to another. An electron goes from one place to another. And an electron emits or absorbs a photon. That's it. 3 actions. And from those 3 actions, you get all of chemistry, all of light, all of magnetism, all of electricity, radio waves, the colors you see, the fact that your hand stops at the table instead of going through it. Olivier, there are no gears underneath, no hidden mechanism. Don't ask, but how does it really work? Because this is how it really works. Photons being exchanged. That's the bottom, that's as deep as it goes. Now, people figured out the complete mathematics for electricity and magnetism in 1873. Maxwell wrote down the equations that unified the whole thing. And this was probably the most fundamental transformation, the most remarkable change in human history. Because once you understand that electrical and magnetic forces are connected, that they're really two aspects of the same phenomenon, you can do things. You can make a current in a wire, create a magnetic field. You can move a magnet near a wire and create a current back and forth. Electricity and magnetism dancing together. Think about what that means. There's a dam somewhere. Water falls, turns a big wheel. That wheel is connected to copper wire spinning near some iron. And because the copper moves near the iron, electrons start moving in the wire. That movement travels through thin copper lines spread across the whole city. And at the other end, another piece of copper and iron turns that electron movement back into spinning motion. All the wheels in the city turn because one wheel at the dam turns. Istopi that one, the all istopi. Start it again. They all start. And what's doing this? Just copper and iron. Nothing else. It's not complicated machinery. It's not some special substance. It's just the fundamental nature of electromagnetism. You move iron here. Iron moves over there, far away, connected by nothing but copper wire. What a fantastic thing nature is. We built everything on this. Lights, machines, all of it running because electrons dance through wires. Now, here's something remarkable. We can calculate how magnetic an electron is. Not guess, not estimate, calculate using just those three simple actions. Photon goes here. Electron goes there. Electron absorbs photon. You add up all the ways these things can happen, all the different paths, and you get a number. And when you measure what nature actually does with very precise instruments, the theory and the experiment match to an extraordinary degree. The difference between prediction and measurement is so tiny. It's like measuring the distance from Los Angeles to New York and being accurate to less than the thickness of a human hair. That kind of precision doesn't happen anywhere else in science. This is the most accurate prediction humans have ever made about anything. And it comes from understanding the electromagnetic force, the same force you felt as a kid pushing two magnets together. So, we can describe magnetism with extraordinary precision. We can predict exactly what it will do. But can we explain why it exists in terms of something more familiar? Oh, and that's not because we failed. That's because electromagnetic forces are the familiar thing that explains everything else. Now, there's a number in physics that nobody can explain. It's about 0.085, or if you flip it around and square it, you get roughly 137. This number determines how strong the electromagnetic force is, how strongly magnets attract, how much electrons repel each other. Everything about electricity and magnetism depends on it. And nobody knows where it comes from. We didn't calculate it from something deeper. It just is that number. If you ask why 137 and not 250, there's no answer. It's one of the great damn mysteries of physics. Where did this number come from? Did somebody write it down? And we just don't know how. If that number were very different, magnets would be stronger or weaker. Atoms wouldn't hold together the way they do. Chemistry would change completely. We probably wouldn't exist. The whole universe, including every magnet you've ever touched, depends on this mysterious 137. Now, I have to tell you something about the history. Because when physicists first tried to calculate magnetic properties of electrons using quantum theory, they got nonsense. Infinity. The equations gave infinity. That's not an answer. And for years, people struggled with this. Then around 1948, a solution appeared. The idea is that we never measure a bare electron by itself. What we measure is always the electron plus all its interactions, all those virtual photons being exchanged. So you start from what you actually measure, and the infinities get absorbed into those measured quantities. Everything comes out finite. It's called renormalization. Some people think it's suspicious, like hiding problems. But the results match experiments to incredible precision. So maybe the nature is. Now, here's something about understanding magnets at the deepest level. The way quantum mechanics works, it's nothing like everyday experience. Your brain evolved to understand rocks and trees and animals, things at human scale. But electrons don't behave like tiny balls. They don't orbit the nucleus like little planets. People say electrons act like waves. Not exactly. Like particles? Not exactly. Like a fog? No, that's not right either. If you want a clear picture of what's happening inside a magnet at the atomic level, something you can visualize, I can't give you one. Nobody can. What we have is mathematics. We write equations, we calculate, and predictions match reality with extraordinary accuracy. It's like a machine that calculates exactly when something will arrive somewhere. It does the arithmetic perfectly, gives exact answers, but has no picture in its head. It doesn't know what anything looks like. It just calculates. We calculate what magnets will do. We're extraordinarily good at it, better than almost anything else in science. But the intuitive picture, the ability to really see what's happening, that's beyond us. Nature, at that scale, is genuinely different from anything we evolved to understand. And that brings us back to where we started. You push two magnets together, you feel that force, and you ask, what is that? And the honest answer is, it's electrons exchanging virtual photons. It spins lining up in iron. It's the electromagnetic force that holds your entire body together and runs the whole universe. We can describe it with spectacular precision. But if you want me to explain it in terms of rubber bands or springs or something you already know, I can't, because those things are explained by electromagnetism, not the other way around. Magnetism isn't the mystery that needs explaining. Magnetism is the explanation. Magnetism isn't some strange, isolated phenomenon. It's part of the electromagnetic force, one of the fundamental forces of nature. Every atom in your body is held together by it. Every chemical reaction depends on it. When you see colors, that's electromagnetism. When you touch something solid, that's electromagnetism. When a compass points north, when a motor spins, it's all the same force. And it all comes from just three simple actions. A photon goes from here to there. An electron goes from here to there. An electron emits or absorbs a photon. That's it. Three things. Chemistry, biology, the structure of matter, it all emerges from these three actions combining in countless ways. There are no gears underneath. There's no deeper mechanism hiding behind. This is how it really works. And we can calculate what will happen with precision that matches experiments to 10 decimal places. Like measuring from Los Angeles to New York, accurate to a human hair. That's not philosophy, that's experimental science. If it agrees with experiment, it's right. Now, does that mean we understand everything? That mysterious number 137, nobody knows where it comes from. We can't picture what electrons actually do at the quantum level. We describe nature with mathematics that works, but our mental images are always approximations. But here's the thing. Physics is experimental. You don't sit around waiting to understand everything perfectly. You learn enough to predict what happens. You test it. And if it works, you use it. That dam with copper, wire-making wheels turn across the city, that works. Because we understand electromagnetism well enough. Not perfectly well enough. And when you asked why magnets attract, you wanted an answer in terms of something familiar: rubber bands, springs, invisible strings. But the answer is that magnetism is the familiar thing. You just didn't realize it. Every time you've touched anything in your life, you are feeling electromagnetic forces. Every solid object, every surface, that's electrons pushing against electrons. You've been swimming in electromagnetism since the day you were born. Magnets just make it obvious. They let you feel, at a distance, what's usually hidden at tiny scales. So, next time you pick up a magnet and feel that push or pull, don't think of it as mysterious. Think of it as nature being honest with you, showing you directly what's usually invisible. The same force that holds your own hand together, acting across the space between two pieces of iron. That's what's happening. That's what you're feeling. And the fact that we can describe it, predict it, calculate it with such precision, that's not magic. That's just paying attention to what nature does and writing it down carefully